Welcome to Ask and Learn.
The speed at the surface of the Earth, so we have the Earth, this is rotating from west to east, is basically given by v is equals to 2 pi radius of the Earth divided by its time period, which is equals to 2 pi 6.38 times 10 to the power 6 divided by 86,400 seconds. If it is one revolution per day, it actually means about 86,400 seconds. If you solve that, you will get 464 meters per second. Now, this is the speed of the Earth at the equator relative to the center of the Earth. We call it eastwards velocity. Eastward, it's plus x, we can say, because the Earth is moving at this speed from west to east. So that is the velocity of any object on the surface of the Earth traveling eastward, basically. The escape velocity at the surface of the Earth is given by square root of 2 gme by r, which is equals to square root of 2 times 6.67 times 10 to the power negative 11 times the mass of the Earth is 5.98 times 10 to the power of 24 and divided by 6.38 times 10 to the power of 6. If you solve that, you will get the escape velocity is 11,182 meter per second. Now, the meaning of escape velocity is that an object has to be given this much velocity in order to escape the gravitational field of the Earth from the surface of the Earth. And now, what they're asking is that with the surface of the Earth traveling east, and in the first case, they're saying that if the rocket to escape from the Earth is also fired eastward, so with the surface of the Earth traveling east and the rocket's velocity to the east, the rocket velocity and the Earth's velocity has to add up linearly to give the escape velocity. So I hope that is clear, which means that the rocket relative to Earth surface, this velocity plus 464 meters per second velocity has to actually give you the escape velocity, meter per second. So if you solve that, then you will get the velocity of the rocket relative to Earth as approximately equals to 10,700 meters per second. That's the first part of the question. For the second part, they say that the rocket, for a rocket to escape if the Earth at the equator in a direction is westward. So with the surface of the Earth is traveling eastward, Earth is traveling eastward, and the rocket's velocity is basically towards the west, then we can say that v rocket relative to the Earth, if you add this velocity to the Earth's velocity, okay, then you should get a velocity of 11,182 meter per second. So therefore your answer will be approximately 11,646 or 11,600 meters per second. So with the surface of the Earth traveling east and the rocket's velocity to the east, in the first case, the rocket's velocity and the surface velocity will add linearly. But for this part, with the surface of the Earth traveling eastward and the rocket is moving westward, the rocket velocity will have to be higher than the nominal escape velocity. So therefore, we get 11,600 meters per second. And in C, when fired vertically upwards, so if the rocket is fired vertically upwards, the rocket velocity and the Earth's velocity are at right angles. The Earth's velocity and the rocket's velocity are at right angles. So which means if you apply the right triangle a law of vector addition. So we'll have v squared rocket relative to the Earth plus 464 squared. That should be equals to 11,182 squared, which is the escape velocity. So in fact, the Earth is traveling this side and the rocket is moving the upwards. Basically, for a person stationary, you will see the rocket is moving in this direction. So that is the escape velocity, which is the hypotenuse, which is 11,182. If you solve that, then you will get v rocket relative to the surface of the Earth is equals to 11,172, which is approximately 11,200 meters per second. So that is the answer to the third part here.